In this problem, a person is holding onto a rope that's attached to a box. The box is dangling off a cliff, and the person is lowering it to the ground with constant acceleration. The person then hits a bit of ice and slides toward the edge of the cliff. We need to determine the velocity that the box hits the ground and the velocity the person hits the ground. Our first issue then is to determine the acceleration of the person-block system when the person begins to slip. We begin by making a free body diagram for both the box and the person. The only force acting on the person once they start to slip is due to the tension from the weight of the box. So even though the person is heavier than the box will still start to slip because the weight of the person isn't influencing the person's horizontal motion, at least not yet. So the free body diagram for the box has two different forces, the gravitational force, or weight, of the box, and the tension provided by the person and the rope. We then write a net force equation for both the person and the box. This is where the fact that the person is heavier than the box becomes relevant. The heavier the person, the smaller the acceleration they'll experience. Both of our equations have the force of tension. This allows us to combine the two equations into one and then solve for the acceleration of the system. This is a place where I sometimes make mistakes because the acceleration is the same for the person and the box, with one exception. The acceleration is positive for the person, meaning they're accelerating toward the right, but negative for the box. That's simply because we make the downward direction negative. Once I account for this difference in sign, I can solve for the box's acceleration. Here, the person's acceleration is represented by A2, and the box's acceleration is represented by A1. Finally, I solve my equation for that acceleration. When I plug the numbers in, I find an acceleration of 0.798 meters per second squared. You'll notice that I did not plug in any numbers until this last step. This helps me keep track of what's going on. And actually, what I ended up doing for this problem was to plug my numbers and equation into a spreadsheet. That way I was able to correct any mistakes in my equation and immediately have a new result. From here, the problem becomes a kinematics problem. In other words, we go back to our original equations for motion and don't concern ourselves with the forces that have set things in motion. The problem gave me the initial velocity of the box as it was being lowered, and the distance the box needs to move until it hit the ground. I also need that acceleration I just calculated. When I substitute my values into the equation and calculate the final velocity, I find that it's 5.2 meters per second. I pause here to think about my answer. If the box is experiencing an acceleration in the same direction as its motion, it's going to speed up. 5.2 meters per second is certainly more than the initial velocity of 1.5 meters per second. So that makes sense. It's useful to look at your answers and make sure they're making physical sense. My last step is to calculate the velocity with which the person hits the ground. I repeat the procedure I just followed and use the same equation. But since the box has already hit the ground, my acceleration is going to change. For the person, the acceleration will be 9.81 meters per second squared, the acceleration due to gravity. Well, I didn't draw it in here. Remember, the person is higher than the box was when this whole calamity began. The original problem told us the cliff was 27.7 meters high. Too bad for the person. When they hit the ground, they'll be moving 23.9 meters per second. You or I would typically only run about 5 meters per second, and the fastest runner in the world has been clocked around 10 meters per second. If you think about running at your full speed, actually 4 times faster than your full speed, straight into a brick wall, you'll realize that this person is not going to have a good day.